Okay, so the initial information that we are given is that we have 3 pieces of standard paper, 8.5 inches by 11 inches, and we are taping them in this formation, an L shape. This diagram is given in the instructions, and we are given that the scale factor is 1 to 64. So 1 inch on our paper is going to be 64 inches in real life. So our initial task is to design a parking lot that maximizes the number of cars that we can park in this L-shaped space. Thankfully, the measurements of standard parking spaces are provided, and it tells us what angles need what amount of space and what aisle widths we have to have with certain lengths of parking spaces. So this chart that they give us is really, really helpful. So the first thing I did was measure that top part of our paper to see about how many feet that is in real life using our scale. To find this amount, I multiplied 8.5 by 64 and then divided by 12, so 12 representing inches, because I want the number of feet, because most of our measurements in our chart in this top right table are given in feet, and I just need a basic conceptual understanding of how much space do I have to see how many, what kinds of parking spaces I can fit. I did the same thing with the length of our paper, which is 11 inches. So after using the conversion, the scale factor, I got that the width of the top of my paper is just over 45 feet, and the length of my paper is just under 59 feet. So this gives me an idea of what can fit where, and I can start thinking about what kinds of parking spaces I want to try and put here. Next, I started thinking about how I view parking lots, in that if it's a one-way design, which I'm figuring that's what I'm going to need because it's sort of a narrow space, I'm going to want parking on both sides if it's one way. So, because I want to try and fit the most amount of cars. So I started multiplying the stall depth, meaning how far it's going to go into the space where people are going to be driving, and I started multiplying it by 2 to get an idea, because if I want it on both sides, it's going to account for twice the amount of space. So if I want parking on both sides, I need enough space to have 2 times the depth of a parking space plus the aisle width, because we need room for cars to drive as well. After playing around with it for a while, I realized quickly that none of these, with 2 times the stall depth plus the aisle width, are going to be less than 45.33 feet. So I'm starting to get a little stuck, because my first idea was that in order to maximize space, I need parking on both sides. It's also at this point that I'm still thinking I want my entrance to be at the top of the paper and the exit to be on the right side. So it's after I've looked at this for a while that I realize maybe it would be better if my entrance wasn't at the top. So I get a little stuck, and I notice on the instructions it says part of the materials is that we can have 8 to 12 miniature cars or paper models of miniature cars, and it gives the dimensions of those, 1.4 inches by 3.5 inch rectangles. So I decide I'm going to make 12 miniature cars so I can play around with them on my paper and see if a visual, hands-on type approach might help me better, because I'm having a hard time figuring out the angles of what things should do or where cars should go. I'm throwing around parallel parking on one side or angled parking on the other side, trying to just visualize everything. I think by making these cars, I'll have an easier time. It's also at this point that I get a little bit hung up on the fact that it says 1.4 inches and how bad of a measurement that is for someone using a ruler. We know that rulers in inches go by 1/16, so trying to convert 1 4/10 into 1/16 we're not going to ever get an exact measurement using our ruler, which is unfortunate. But this could lead to really good conversations with our students about the inaccuracies involved with not using the metric system or being given measurements in ways that are really hard to convert. So I decided to estimate because I knew that 1.5 is halfway between 1 and 2, obviously, and that would be 8/16. And then the next little notch down is 1.375. So I kind of wiggled it and estimated about what 1.4 would be, being a little bit closer to the 1.375 than the 1.5, but still knowing that it's not exactly accurate with the tools that we have. I used index cards here to be a little bit thicker than the paper, so it would be easier to tell. But here it's hard to tell because they're both white. When I do this in class, I will use probably colored cardstock and maybe even laminate them so that I could use them for several years in a row. And it would be easier for the kids to see the cars on top of the paper using colored paper instead of white paper. And also a thicker version like cardstock or laminating the cardstock. I'll speed up this next part so you don't have to watch me cut paper. Now that I have all my cars cut out, I am just going to play around with them on my blueprint of my parking lot just to see what will fit where and just trying to play around with it. I also have to keep in mind that even though these are supposed to represent cars, it's not necessarily the amount of space in the parking spot because as we know, we drive cars, the parking spot should be larger than your car. So we know that the parking spot is going to take up more space than just the car is. We can't just pack all the cars in there really tight. So that's another thing that we have to keep in mind whenever we are doing these. Also, we have to remember that the width of the lines are going to have some area. It's not just a tiny little line. So we have to think about that as well. As you can see, I moved on to the other side of my parking lot as being my entrance, and angling my parking towards that direction. I realized that the width of this entrance is much wider because it's the long end of the paper, so I could possibly fit 2 sides worth of parking. And I did a quick double check to make sure that 2 rows of parking would fit, as well as an aisle width. Here I've zoomed in a lot into this bottom right corner to show you how I played around with the different angles. I first started with a 45-degree angle for no particular reason. I just started somewhere in the middle to get an idea of what that looks like. I'm a very visual person, so I kind of need some examples before I can commit to something. So the first angle that I drew was 45, and then I moved on to a 30-degree angle and drew that one in. The last angle I was going to play around with was the 60-degree angle. So I use my protractor again to find that angle. I've noticed that the steeper my angle, so as I go from 30 to 45 to 60, I can get closer and closer to the edge, so hopefully fit more parking. It's also at this point that I realized that the most cars I can fit is going to be at a 90-degree angle, if I could just stack them all in there, but our space here doesn't allow for that because there wouldn't be enough room to have 2 rows of 90-degree parking and an aisle in the middle. When we have 90-degree parking, our stall depth is 18 feet and the aisle width is the largest aisle width that is available on the table at 24 feet. So if we had 2 sides of stall depth 18 and an aisle width of 24, that would be 60 feet. And with our scale factor, our 11 inches translates to about 58.66 feet. So we are just shy of being able to do 90-degree parking. My next thought would be the next best thing is 60-degree parking. So unfortunately, when we have 60-degree parking, our stall depth is 21 feet and our aisle width is 18 feet. So if we have 2 aisles of 21 feet and an 18-foot aisle width, we are back at 60 feet, which again is still bigger than our allotted space of just over 58 feet. So I decided the next best thing would be 45-degree angle parking. With 45-degree angle parking, we have a stall depth of 19 feet 10 inches. So if we have 2 rows of parking, we'll need 2 of those, plus an aisle width of only 15 feet. That puts us under our 58.66 feet. So this one will work. So next I decided to convert my little fake car piece into what it would be in real life, because I'm just curious what size car would need to go and what size space, because I know that my stall width needs to be 9 feet, but I'm just curious what size car this piece of paper is going to represent. Now, in order to draw my blueprints, I need to convert these values in the table for lengths into values that I can use to draw. So in order to do that, I need to take the measure that they've given me. So for example, my stall depth is 19 feet 10 inches. So I took 19 feet and I multiplied that by 12, and then I added the 10 inches. So now I have my stall depth in inches. Then I divided by 64 to get back down to my scale factor. So now I have the number of inches that it's going to represent on my blueprint. I completed the same process for every measurement I had to put on my paper. I took the value they give us in feet and I multiplied it by 12 to convert into inches. Then I divided by 64 to get down to my correct scale. So I did that for any value I was trying to find that I was given in real life that I needed to convert back to my paper. It was here after marking off the stall depths I would need that I noticed that my aisle width would be a little bit larger than necessary, but as we know, as this relates to real life, our aisle width can be larger than necessary, but it can't be smaller than necessary because these are standards that are set by either national standards or state standards, and it's important that we are within those standards. So it's okay if we have more room to park our car, but it's not okay if it's too tight because then we're not in regulations. So this would be an interesting thing that might come up in class that we could talk about with our students. I decided to do this angled parking all the way up the left side and then all the way up the right side until I got to that corner. As you can see here, I'm measuring my stall width of 9 feet that I've converted into inches on my paper and scaled it down to my scale factor of 1 to 64. To do this, I'm making sure that my measurement here is perpendicular to the line of my lines on my parking lot. So I need to make sure that my width is accurate. I can't just measure 9 feet at any angle. It has to be the exact width. So we have to make sure that we stay perpendicular throughout. As you can see here, I really want this 2 car that's labeled 2 to fit in that last little triangle, but it won't fit, so I just have to give that space up. Now I decide to fold my paper over to draw the other half of my parking lot, slightly because I'm a little bit lazy and I don't want to measure out all of those 45-degree angles again, but also because I want it centered. I would like my aisle in the center, and I know that a 45-degree angle reflected over is still a 45-degree angle. Okay, now that I have my 45-degree angle parking, I'm going to play around with my fake cars again and see what kind of angles will work best here. I noticed that there's no way for me to do parking on both sides of the street. Even though I try parallel parking, it just won't fit. So I decide that the best option is my 90-degree angle parking, because those I can fit as many as I can in a row and only do them on one side. So here you'll see me measure this length several times. For some reason, I kept doing it differently, but I finally got it right by the end. I measured the stall depth I would need for a 90-degree parking and the aisle width I would need for 90-degree parking, and as you can see in that little corner, there's a tiny bit of overlap in that little corner of my last angled parking. So this was a little frustrating for me because I really wanted it to fit, because technically it's not in regulations if it's overlapping, because there's that little bit of space that there is not an aisle width of 24 feet if we have that last angled parking there. So as a student doing this project, I would like to argue that this spot could be a space for a compact car or maybe a motorcycle or something. It would break my heart if I would have to delete that entire parking space over like a tiny little corner. But I do think that this tiny corner would lead to some really cool conversations with students about what's important or what we could do to remedy the situation, or if we could remeasure something or try and work around it to try and fit one more space in. As you can see here, I've started to draw in my 90-degree angle parking spaces. They're all the same width, and this one's a little bit easier to measure than the 45-degree angle ones because they are already squared up and at a right angle, so I just need to measure the width of each one along the end of my row. And as you can see, I have eliminated my parallel parking that I once had there on the side, realizing that it's not going to fit as much as I wanted it to. So, to truly be done, we need to answer those few questions that we were given in the project. The first question, well, not the first question, but one of the questions asks us for the flow of parking, and I originally had the flow of parking going the opposite direction, but after measuring different things, I realized that this direction was most advantageous to fit the most parking, because I could fit angled parking on both sides from the entrance. My scale factor was 1 to 64. So, like I explained before, in order to find the measurement on my paper, I needed to take the measurement I was given in feet and multiply it by 12. Then divide by 64 in order to give us the length in inches on our blueprint. Last, I count up my spaces, and I have 9 spaces at a 45-degree angle and 10 spaces at a 90-degree angle for a total of 19 spaces. And remember that one of our spaces in that angled parking is a little bit special. It can be marked for a compact car or something, but we decided to let it slide, and as a student, I would argue that this space could be counted. Overall, I think this was a really cool project, helping students with geometry, with drawing angles, with measurement, with scale factor, and converting measurements. I also think it's a really great example of when group work is really helpful. I actually was really stuck on this idea of starting my entrance at the top and my exit at the right, and I was working on it, and my husband just said, well, why don't you just enter from the other side and exit from the top? And it changed my whole perspective, and I'm really excited to see how the kids can work together to come up with a solution to this problem.